Hello everyone, welcome back. We're going to start our second official lecture, if you like, for the online packets. We'll see, hopefully you got this one in front of you. Remember to, if you can, print these out and fill them in as we go through them on the video. That's by far the best way to learn this material, okay? Alright, so the components of matter, hopefully you've done the background reading for this, okay? So chapter 1, sections 1 through 5. Just to recap, we're going to go through the packet together right now. As soon as possible after we finish the packet, come back and do these homework questions from the back of the book. Now remember, these are chapter 1, question 37, 39, etc. Okay? Try and do as many as you can. The answers are in the back, so check the answers. If the answers aren't the same, then that's something to kind of bring to an office hour. Remember, office hours Thursdays at 9 on Teams. Okay? Alright. If you happen to have a different textbook, a different version of the textbook, it's not a problem, okay? General chemistry textbooks are all pretty similar. Just make sure, you're looking at the right material because it'll look familiar, and then just try some questions from whichever textbook you happen to have, okay? Now, so let's go through it. First things first, it's kind of a review, really. We talked about it in the last packet. What is matter, okay? And if I use my MTV word, matter is stuff, right? Physical objects. What defines a physical object? Anything with mass and volume. It has to have both, okay? It has to have some weight and it has to have some shape, all right? All physical things have mass and volume, okay? So stuff. So the stuff around us, just look around the room right now. Everything is matter. Everything you can see is made of matter. Okay, it has those two physical characteristics. It has mass and it has volume. Okay, now, of course, chemists study matter and its properties, as we mentioned in the last packet. Okay, and of course, so the changes matter undergoes, call those reactions, and the energy. The heat comes out, like when you burn a piece of wood, or heat goes in when you make an ice. Sorry, heat goes out when you burn a piece of wood. Or if your heat goes in when you melt an ice cube, something like that. So we look at the energy changes associated with those processes. All right. Now, as you probably already know, this is kind of simple, kind of almost kindergarten stuff here. There are, as you probably learned before, 3 states of matter. But let me put a little asterisk next to that. There are actually 3 stable states of matter. Okay. Stable means you can put it in a jar, come back tomorrow, and it'll still be there. Okay. So there's solids, liquids, and gases. Now, one of the reasons we chose the Trow textbook for chemistry at JJC is because of Trow's true chemical nature, if you like. He likes to look at a relationship between macro and micro. So if you have some kind of, blocks of, maybe they're little gold bars or something, right? Some kind of solid chunks or cubes of matter in a test tube like that, if you zoomed in with an STM, one of those really powerful microscopes, you'd see the individual atoms sitting there, okay? If I had a liquid, like a glass of water or something, zoomed in, that wouldn't be a glass of water because these are atoms, but some kind of atomic liquid, there they are, individual atoms right there. You have to excuse my phone, all right? And finally, gas. Well, this is kind of not to scale, because as we'll talk about later, the separation between particles and the gas is very large compared to their size, but it kind of shows you how things are kind of inside matter, okay? We'll talk about this more on the next page, but these are very close together, a little bit further apart, and very far apart, okay? Now, I said stable, right? Are there any other states of matter? Let you think about that for a second while I drink my delicious coffee, right? So, are there any other states of matter? Well, the answer is yes, okay. The other state of matter is plasma. Now, let's write it down. I'm going to do it on the same page you guys are. Plus plasma. Plasma is basically a high energy, low pressure gas. If you own a plasma TV, you own plasma, okay? If you own a candle, you can make plasma. What is plasma? It's basically, what is a flame? A flame is plasma, okay? What is the bright dots on your TV when you turn the TV on a plasma TV? That's plasma. It's basically a little kind of space where you have a low pressure gas and then you zap it with a lot of energy. Okay, so think about a candle flame, or zapping the gas inside a little ampule in your plasma TV, super high energy, and it breaks apart. So basically you break the part into tiny pieces, you break the gas into subatomic particles, essentially atoms, ions, things like that, electrons, and that gives out a lot of light. Okay, so a high energy busted apart gas is a plasma. The surface of the sun is basically plasma. Okay, can you keep it in a jar and come back tomorrow and look at it? No, it's not stable. Okay, you can't store it, you have to make it. So you turn your TV on, you light a candle, you make plasma. So it's not classically one of the three states of matter because it's not stable, although we do classify it as a state of matter for completeness. Okay, now when we get back to those three states of matter, the stable ones, okay, remember as chemists we're always about relating macro and micro, just like Tro did on this first slide here. So you might want to keep this one to the side so you can see it, because it makes a lot of sense, right, when you look at these things here. Maybe I'll keep it on the side too and come back as needed. All right, so what we're going to do, we're going to relate macro and micro just as a chemist would. Okay, and you can go in either direction. Okay, we're probably familiar more with macro, what we see with our eyes, and then talking about it in terms of a microscopic model, but you may go the other way as you become more chemistry-ish, right, if that's the word. All right, so solid. Well, what makes a solid? Well, think about a solid. Hold a solid in your hand right now. It keeps its shape, right? It has a fixed volume, right? Okay, so fixed volume. And shape. You can't really deform the shape of a solid, right? Well, we call that a special word. Solids are rigid. They have a fixed volume and a fixed shape, and their shape is invariant. You can't change the shape. We call that rigid. That's a key word, rigid, right? Now, here's the big question. Why is it that a solid is rigid? Why is it kind of hard to, break, essentially, right? Okay, let's go back to the picture. So here's our, I forgot my timer, but we'll keep going. All right, so here's my picture. Okay, if I zoom in and look at the particles in a solid compared to a liquid or a gas, what do we see? We see the particles are actually touching. Only in a solid are the particles touching. All right, particles touching. Okay, therefore, because they're touching, they're the closest distance. You can't get any closer than touching, right? Okay, now here's a kind of a key fact. The shorter the distance between particles, the stronger the bond between the particles. Think about people, right? So if you're standing right next to someone, you can give them a hug with two arms, and that's a strong bond. They're not going anywhere, right? Okay, so it's a truism of nature, close equals strong, right? Okay, so particles are touching, closest distance, it's the strongest bond. Okay, now think about that for a second. I'll tell you a little story. Well, that's kind of a made-up story, but I'll tell you a story. So imagine you're a kid, right? And there's some truth to this. So you have a box of Legos, and you take like half an hour and you build this really nice tower of Lego blocks, right? And then your kind of mischievous younger brother comes in and pushes over your tower. What happens? Well, the tower topples over and smashes into 100 pieces of individual Lego blocks, right? That's a pain, right? That tower was not rigid because the bonds between the Legos weren't very strong. Even though they were touching, like the atoms in a solid, the bonds weren't very strong. Now think about this. Next time you're wise to it, right? So you make your tower, but every time you put one Lego and click it to the next one, you put a little dab of super glue on the Lego. So you super glue the Legos, right? So then you build your tower with these super glued Legos, and your mischievous brother comes in and knocks over the tower. What happens? Answer, the tower remains intact, right? You can't break it apart. It's rigid. So if you think about it, because that bond is so short, it's so strong, a nice way to think about that bond is super glued Legos, right? That's why solids are rigid, because the atoms are super strongly put together. If I just have one super strongly bonded atom to the next, to the next, to the next, over a long distance, that structure is really strongly bound. It's rigid. It can't be broken. That makes sense. All right, fair enough. So solids are rigid because the particles are touching. All right, strongest bonds. If we look at the liquid now, In a liquid, there's a slight separation. Okay, it's a slight separation. And that's actually what happens. So we can go kind of backwards. Slight separation between particles. Fair enough, right? Okay. What that happens is slightly weaker bond than the solid. They are technically still touching. The particles in the liquid are all touching, but they can tumble over each other. That's kind of the thing. Think of like having a line of people and running down and giving everybody a high five. You're always in contact with someone, but you're able to move. And that's kind of how liquids are. Okay, they're always doing the high five thing. So they're just slightly separated so they can kind of move past each other, but they're still in contact. Okay, so if we think about that now, a nice way to think about this is to get a bunch of marbles, maybe just kind of do this thought experiment in your head. Get a bunch of marbles, put them into a beaker, yeah, and then pour the marbles out of the beaker into another container. They'll tumble over each other, right? They'll still be in contact, but they won't be, you know, stuck there solidly, so to speak, right? So that tumbling is what leads to fluid behavior, right? So liquids are fluids, right? Because on the microscopic level, the particles tumble over each other. Just think about pouring out a bowl of marbles, right? That means they have a fixed volume, right? A pint of beer is a pint of beer. It doesn't matter what container you put it in, yeah? But it takes the shape of the container. So liquids have a fixed volume and, of course, a fixed mass, but they take the shape of the container you put them in, because if you like, all the particles get into all the nooks and crannies, if you like, right? Okay, so why are fluids fluids? Because they have a slightly weaker bond, slight separation. And think of tumbling marbles when you pour out a jar of marbles. All right, now finally the gas. Now we can't, you know, should we be in class, I'd do a very dramatic kind of in-class demonstration where I end up walking out of the classroom for educational purposes, right? So if you look here on the atomic scale, it looks like there's probably 2 or 3 diameters, you know, atomic diameters between the particles and the gas. That is wrong, 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 wrong. There's actually many thousands of diameters between particles in a gas, right? So if you have a gas particle, the next one is maybe 1,000 atomic diameters away, right? That's important because if they're so far away, very distant, therefore no bonds. It's like trying to shake hands with someone in Paris, right? It's just too far away to make any kind of meaningful contact. Bonding happens within an arm's length, essentially. If you're like 3,000 miles away, you can't make a bond, right? Okay, so there's no bonds between particles in a gas. All right, now remember, that's nothing we can actually draw to scale. You know, the next one's probably over in my kitchen over there, right? You can't see the kitchen, but it's over there, right? So we can't draw that, but just assume that's true. Okay, so the spacing between particles is very large, so there's no bonds between the particles. So what do you think they do? If there's nothing holding one particle to the next, they just fly off and keep going, yeah? And they keep going until what happens? Until they hit the sides of the container they happen to be in, all right? Okay, so gases have no fixed volume or shape. They basically fill the container they are in, okay? So gases have no fixed shape. They just fill the container they're in because there's nothing holding one to the next. They just fly off until they hit the walls of the container they're in. So it's not really right to say what's the volume of a gas. It's really right to say what's the volume of the gas is container, or I should rephrase that. What's the volume of the container the gas is in? That's the volume of the gas, right? And it doesn't matter how big that container is. It can be a room, it can be the whole planet's atmosphere. There's a classic example in the book of Julius Caesar. So Julius Caesar was stabbed on the steps of the Senate. His last breath, tu brute, right? And that last breath went out into the atmosphere, right? Now, if you do the math, if you count the number of nitrogen molecules in that breath and then spread them out through the whole atmosphere, every time we breathe in literally 2 or 3 molecules of Caesar's last breath, which is kind of interesting, okay? So gases fill the container. It doesn't matter how big that container is because they just keep going until they hit the walls. All right, so those are the three stable states of matter. Hope that makes sense. Okay, oh, you know, we're not going to talk too much about plasma. We'll keep it to the stable states. Now, obviously, the state of matter, and we'll talk about that. Kind of forgot to mention it, but it's kind of an obvious one. So this is a solid, state symbol L, liquid, and gas. All right, so we put the state symbol as a subscript after the formula, denoting if it's a solid, a liquid, or a gas, right? Okay, so the state of matter depends on the forces, right? If it's a strong force between the particles, it's a solid. If it's kind of medium, it's a liquid, and if it's none, it's a gas. So the state of matter entirely depends on the strength of the bonds between the particles in the matter, all right? So if we look at a classic, which is H2O, right? So here we have ice. Below 0 degrees C we have ice, okay, and then we have water, 0 to 100 degrees C, and then above 100 degrees steam. So that's a solid, a liquid, and a gas. As we increase temperature, and you can make notes on the side here, what's happening? So think about that. As you increase the temperature of an ice cube, what happens to it? Well, it melts, doesn't it? Okay, it melts at exactly 0 degrees C. Why is that? Why do things have particular melting and boiling and freezing points, things like that? Okay, because that corresponds with the strength of the bond. Okay, so I like to think about snapping a twig, right? So I get my ice and I get it to 0 degrees C. I've got just enough thermal energy then to snap that twig, right? So I weaken that bond, turn a strong bond into a weak bond. Then it's water, right? They're slightly more separated, weaker bonds. And I get to 100 degrees C and I snap that final bond and they just fly off to make a steam gas. Okay, so just to answer the question, rank the intermolecular forces present in steam water in order of increasing strength. So as the strength goes up, what's what? Okay, so what has the strongest bond? Ice. What's the weakest bond or no bond? Steam. Water's in the middle. Okay. Stronger bonds. Okay. Okay. And as you go that way, as temperature increases, you have to break those bonds, right? So you eventually turn ice to water to steam. Okay. So, kind of formalize that a little bit here. So to change between the states of matter, all you're doing on the microscopic level when you melt something, when you boil something, okay, all you're doing is you're changing the nature of the bonding between the particles, all right? So think about melting. What do? It's going from solid to liquid, right? So your strong forces between particles, better way to say it is weakened, right? Weakened. So I turn strong to medium force, if you like. Therefore, particles can now tumble. So instead of being in that rigid kind of framework of atoms we call a lattice, we'll talk about that in a minute. If they turn into a liquid, they can tumble over each other. Okay, so melting, solid to liquid, rigid material to a liquid material. And then finally, boiling, which is of course liquid to gas. Those medium forces in a liquid are broken. Particles, nothing connecting one particle to the next, particles fly off, fill the container. Okay, hopefully that makes sense. Changes of state, types of matter, it's all about the strength of the bond between the particles. All right, there's a nice picture. This isn't a Trove picture, it's one I borrowed from the internet somewhere. Okay, if we look at it, we have the liquid particles, there they are. And then, you know, this obviously is a bigger distance because you can't get that on the picture, but these are, you know, many thousands of diameters now. Okay. All right. So that's states of matter, nice and easy. Hopefully you remember that from a previous class of some sort. All right. Now, our next thing, and I mentioned this in the last packet, there are two types of property associated with matter, okay, chemistry study of matter and its properties. There's physical properties and chemical properties. What's the difference? And give some examples, right? So here's a great way to think about it. If you've ever played this game, you know exactly how this works, okay? It's called Guess Who, right? You ever played Guess Who? Just to recap, you get a bunch of cards, right? And each card has a different face on it, yeah? And the idea is that you kind of identify the one person they've chosen by guessing, right? And you say things like, oh, does a person wear glasses? Yes. Okay, so you can eliminate some people. Does the person have red hair? Yes. Eliminate some people. And eventually you get to a unique set of physical as-is properties. That's what people have, physical properties, as-is properties, right? And it defines you, right? So I'm 5'11", green eyes, English, right? Those are 3 properties about me. If I kept going, I'd eventually become unique, right? So every person has a unique set of physical properties which render them unique, as do chemicals, okay? So, water, for example, clear, colorless liquid, physical property, right? But so is alcohol. Alcohol's clear and colorless, right? Water's tasteless. Alcohol isn't. Water freezes at 100, boils at 100. Freezes at 0, boils at 100. Alcohol boils at 76 degrees C. So as you get into the details, as you get in there, you'll see a unique set emerge, right? Okay, so chemicals are just like that. So it's an as-is statement. You know, color is a physical property, smell is a physical property, all right? Just tell me something about it just looking at it, right? So that's physical properties. Chemical properties, on the other hand, are really reactions, right? So we're looking at change. When we see change, we see a chemical process. Now a chemist, if I take some iron and I turn it into rust by adding oxygen, that's a chemical change. So a chemical reaction, when I make a new formula, Fe is not Fe2O3, is it, right? That's a change, right? So a reaction is a chemical property. So when I'm listing chemical properties, I'm really listing the reactions a chemical does, okay? So here's my car door. It's made of iron. It turns into rust, right? Okay. Is it going back? No. So the arrow is important. Turns into, right? It doesn't come back. It turns out that if it's a reversible change, like melting and boiling and things like that, that's a physical property. We'll do that in a minute, right? But if it's permanent, it's chemical. All right, with those those kind of facts in your head, let's look at this list here, okay? So we'll just go through, and if you wish, pause it to think about it before writing an answer, all right? Okay. So diamond is the hardest substance known. This is true, diamond is the hardest substance. Is that a chemical or physical property of diamond? It's physical. Hardness is a physical property, right? Okay, if I scratch glass with a diamond, the glass will scratch, the diamond will not. That's because diamond's harder. The process of scratching doesn't turn the diamond into something else, right? So it doesn't change, so it's physical. All right. Now, kind of a funny story. Several years ago, I had a student, Chemistry 100 student, come running into my office, and they present me with this, what looks like a diamond. I found this in the Joule parking lot. Is this a real diamond? And later on we're going to do a density experiment. You can tell something, again, density is a physical property, right? You can tell something's identity sometimes by its density. All right, so go, oh, okay, we'll just do the same density experiment we did in class the other day. We'll find out its mass, find out its volume, and its density. Look it up, I'll tell you if it's a diamond. Awesome. And then we look a little bit closer at the diamond, and it's covered in scratches, and then you get to that whole kind of simple idea that, hey, where'd you get this diamond from? Oh, Joule parking lot. Well, either two things are going on. Either the Joule parking lot is made of diamonds because this thing has scratches, and anything that can scratch a diamond is another diamond, or it ain't a diamond. Okay, obviously it wasn't, because it had scratches. All right, next one, we saw this reaction earlier. Charcoal, which is just carbon, burns in oxygen to make CO2. Did we make a new formula? Yes, we did. So that's a chemical process. All right. Now, next one. Statue of Liberty turned green. Now, this is an example of what copper does. If you've got an old penny, I have an old penny sitting on my garage floor in a crack that I've just kept there, right? And it's turned green over time, yeah? If you look at the Statue of Liberty, it used to be a bronze color because it was made of copper, right? And it's eventually got this kind of coating of green stuff on it. If you look at the roofs of certain buildings which are made of copper, right? Like actually at North Central College they have these roofs, and other small colleges around, and Naboo, right, if you're fan of the Star Wars universe. These green roofs, right, Statue of Liberty, same thing. Copper turns green. Well, why does it do that? It's actually a chemical reaction. I won't do the whole thing, right? I won't balance it, but basically you're making copper oxide, right? And that stuff is the green kind of coating on a copper object, on the penny, on the Statue of Liberty. Okay, it's like a tarnish, right? So is that a chemical or a physical process where the copper turned into copper oxide? That's a chemical process. You can't make it turn back, right? You can't make it turn back. You can scrape it off, but then you just get rid of the stuff, you don't change it back. Okay. Next one, think about this. Copper is a good conductor of electricity. Why is that true? Well, we'll get to that later. It's the metal, it's the property of metal actually, right? It's a good conductor of heat and electricity. If you're into kind of cooking, you might have some copper pans. They conduct heat really well. Copper wires in your house conduct electricity really well. When you turn on the electricity in your house, or you cook an omelet on your stove in your copper pan, does it turn into something else? Does it turn into lead? No, right? Okay, so just by conducting heat or electricity, it doesn't change its formula, so it's a physical property. All right, now next two here, these ones are kind of interesting. I kind of alluded to it above, right? We have a kind of a slight kind of fine print when it comes to physical and chemical properties. When it's chemical, it has to be a permanent change. It never comes back, right? But if it can come back again, it's physical, all right? So sugar dissolves in water. If you think about sugar, C6H12O6 solid, that's your sugar cube, right? And I can dissolve it in water to make C6H12O6 aqueous. It's actually stuck to the water molecules, not itself. That's another state symbol we'll come on to later, aqueous, AQ. Literally means with water, right? Now, if I took my sugar water, or I can do it with salt, whatever I want, right? And then I just slightly heat this thing up and the water evaporates, what am I left with? At the end of the day, all the water evaporates, I'm left with sugar crystals, or if it's salt, salt crystals, so it comes back. That's what we call a reversible process. It has a kind of a double-headed arrow, right? That reversible process is not permanent, so it's physical, okay? Same thing with ice, right? I can get an ice cube out, warm it up, I can get the water, cool it down, that's also reversible, right? So H2O solid, H2O liquid, and if I go all the way to steam, H2O gas, that's always reversible. I can melt, I can boil, I can condense, I can freeze, right? That's a physical process because the formula didn't change. That's a nice way to think about it. The state symbol can change, but the formula cannot. If the formula changes, it's chemical. If the formula stays the same, it's physical, all right? State symbol, yeah, it can change if it's physical. All right, so a little bit of extra credit. Now this thing's going to be, what's the day today? So you're supposed to look at this on Wednesday. So if you kind of send me this by 11:59 on Wednesday, think up two more. If you can look up two more, I'm going to say physical properties, all right? Just send me an email, 2 physical properties, 1 point of extra credit for each physical property. Not ones we've done, so you can't say melting, right? You can't say conductivity. You can't say any of the things we discussed. New physical properties, right? As is. Okay. All right. We're up to 28 minutes. Okay, I think I'm actually going to stop there. Fortunately, I just realized I have a timer on my good old GoPro over here. Okay, so we're about to run out of time, so I'm going to stop here and we'll start the next one, elements and compounds, in a moment. Okay.